the next topic is reference solar cells. So, I told you about some simulators. I told you about the way how to control the spectrum match, the main requirement, like uniformity, spectrum match. But you have to, first of all, for any simulator, you have to adjust the intensity, because in any case, it depends on many factors, like distance between the source of the light and your working place. And you have, in any case, to adjust the intensity. It's not a spectrum, just intensity. But to adjust intensity, it means that you have to use something that will give you information that you should be sure that the intensity really corresponds to the standard or reference condition. That, for example, it's 1 kilowatt per square meter. So, for this reason, you should to use reference solar cells. So it's not some photodetector or so. So we can use some internal source, some internal detector or something to control the intensity, to give some ideas. But if you want to perform the correct measurement, you have to use a reference solar cell. There are different requirements for the solar cells because it depends on the application. But the main reason, the main idea that it should be packaged to protect against some water, some dust and stress, mechanical stress. I mean, because actually it's something you have to care about its working, because it's quite, I would say, important thing in a meteorological point of view, because you know exactly the value of the photocurrent which corresponds to reference condition. For example, 1 kilowatt per square meter of the M1.5 G. And if you have some, I don't know, some dust, something which can change this value, it's, you see, your measurement would be not correct. So you have to protect it. Don't break it, because it's very expensive thing. So it's to avoid any mechanical stress of this solar cell. So it's really protected. Another thing that as I told you, any parameters of the solar cell depends on temperature. And you have to produce the conditions, the reference condition. Normally it's 25 degree from point of view of the temperature. So to provide this condition for the reference solar cell, you have to use some temperature controller, something to control the temperature. But this reference solar cell should have some temperature sensor which is inside. And the temperature sensor, normally it's a platinum resistance resistor, which is some kind of meteorological standards also. It's PT 100, normally it means that this resistor has 100 ohm at 0 Celsius degrees. There could be another requirement concerning electrical switching, but it's not so strict. I mean, you can ask for probe terminal. I will describe it a little bit later why do you need for probe terminal, but it's just maybe to calibrate your IV measurement devices. It's not really required for to calibrate intensity, because to calibrate intensity you need just to measure the current of this reference solar cell. And so there are some standard set of the size. The most common is 2 by 2 square centimeters, like here, but you can find different sizes for M0 application, so it depends on the application. And here is the example again of another solar reference cell. Here you can find some specification to order. So first of all, you have to choose the material of this solar reference solar cell. It's one important thing, because as I will describe later, the spectrum of sensitivity of such a reference solar cell normally should correspond to the spectrum of the measured solar cell. So it's one of the reason to choose the material. But in other case, it should be stable in time, because otherwise it's not the reference solar cell. It's something strange. And of course, normally it's made of crystalline silicon. But you can buy, you can find 35 cells also, like gallium arsenide mostly, but crystalline silicon is the main. So the area, so normally it's 20 by 20 millimeters. I mean the area of this solar cell. Then a dimension, so it's just to you to understand the operating temperature, some kind of range, but you should provide the temperature of 25 degrees. And again, how to connect it. You see, it could be 4-wire or 2-wire. And another thing you have to choose correctly is a protective window. As I told you, it's packaged, so you have some window. In case if you don't need to change the spectrum, for example, you would like to measure silicon-based solar cell, so you just order silicon-based reference cell, and you can order quartz protective window. So you are. But if you want to change the spectrum, you can change another window, so you can change some filters. It's a way to vary. As I told, for temperature sensor, it's some kind of standard PT100. It's a platinum resistor type of sockets, just to get the possibility to provide this similar connections. And calibration, of course, because actually you buy this reference solar cell to provide some condition. It's to calibrate the intensity of the simulator, but intensity of the simulator, this standard 25 degrees temperature, and of this of some spectrum, because if you want to provide the condition of the M0, so you have to ask for them. I mean, if you have another spectrum, for example, you have a simulator and you change the optical filters to M0, and then you try to calibrate the intensity, and you get so you adjust the intensity to get this current. It doesn't mean that you would have this intensity, because this intensity, 1 kilowatt per square meter, would be achieved only if your spectrum corresponds to this one. It's, I mean, one quite important thing, the spectrum and the reference also. And here is some kind of paper. This is a copy of the paper you would have with this reference solar cell, and actually the most part of the price, it's this this value. Actually, it's a short circuit current. Sorry, maybe not this. Here it's, but so I mean, maybe it's the maximum power point. Yes, this value. It's a short circuit current, which corresponds to standard some reference conditions. Because first of all, you have the main reason of this. So why do you need it? You need it to adjust the intensity of the solar simulator. So you put it and measure the current, and when you reach this value, so you can say that, okay, now I have 1 kilowatt per square meter. Then if you want, you can also check another parameters, but it's just to test your IV curve measurement system, but it's not so strict. I mean, the main thing is this value. So it's more or less simple for single junction solar cell. I mean, you adjust the intensity and it's okay, you can measure the IV curve. But if you have a multi-junction solar cells, the things are more interesting. So the main reason is that if you have a multi-junction solar cells, so if you try to present some equivalence circuit, you can consider, for example, for triple junction solar cell, 3 solar cells which are connected via tunnel junction. So the main idea is that you have 3 sources of the current, but they are connected in series. So as we described during the practice, the current is limited by the minimum current. So it means, again, the current is equal for each junction and is limited by the minimum. So it means that if for some reason one of the junction absorbs less light compared to reference condition, in this case you would measure something, the current of the whole device would be lower. So you would underestimate the potential of your solar cell. It means that, again, so you can design your solar cell for reference for real spectrum, for solar spectrum. But if for some reason your simulator, solar simulator, do not provide exactly the same spectrum, and there is some difference in some range, for example, for let's say the simplest case, as I told you, you have some simulator which is in the range of, for example, 300 to 1100 nanometers, for example, using LED, and you try to measure the IV curve of a triple junction solar cell based on germanium substrate. So the bottom germanium subcell would get much less light compared to the normal case for normal solar spectrum. And in this case, if you have, for example, half of the light have half of the current, and in this case you would have half of the total current and your efficiency would be half. So I mean, it's quite important thing, the spectral match, for multi-junction solar cell. So, and it means that you have to get some ideas about your solar simulator. How does it correspond to your measured solar cell? The spectrum for each junction. So actually for this you use a set of reference solar cells, and for each measured subcell you should have your reference solar cell. So I mean, for each subcell. So if you have a triple junction solar cell, you have to use 3 reference cells. And some formulas, just to be more formal. If we want to define the spectrum of solar cell for multi-junction solar cell, when you have a G number, it's not number, it's the index of the junction. For example, if you have a triple junction cell, so G would be 1, 2, 3. So for each subcell, so junction G, the current is determined quite simple. So you have to integrate the product of intensity of the light and the spectrum of your solar cell. Now, if you want to estimate, to calculate the current of a subcell under reference condition, so you use here the reference spectrum. So I mean, so it's a standard spectrum where you can find any source. And of course you use this spectral response of the subcell. In this case, you would have some estimation of your short circuit current for each subcell. So the real short circuit current, I mean, because the short circuit current is something you can measure, so the real short circuit current is the minimum current of the set. You should understand. But first of all, you have to estimate the current of each junction. And if you have a multi-channel simulator, so you can adjust the spectrum because for each junction you can calculate the current. So you should know the spectrum distribution of your simulator. And here things becomes a little bit more interesting. So you have several junctions and several channels. So G is the index of the junction, I is the index of the channel of a multi-channel simulator. And then for each top subcell, for each junction, you can estimate, you can calculate the current, and you can adjust the spectrum using the intensity of each channel so you have a possibility to adjust. system a little bit more complicated because you see it's easy to adjust for one junction, but it's quite just you need only one. Actually, for one junction you need just only one channel to adjust intensity. You understand? But it's more complicated even if you have two junction and two channels. So you make some iteration because you provide some set of the intensity for one junction, but it doesn't cover to another one. So you see, but in some ideal case, you can get that this current of each junction corresponds to the current of the junction which generated when your junction is illuminated by reference solar cell. Actually, for this reason, you use reference solar cell, and then you should adjust the intensity in order that so you know the say current. Here it's the current of the reference solar cell for this condition, and then you adjust the intensity of the channels to get the same current. If you have a for example double junction, so you have two reference cells and you make this procedure. But if you have only one channel, or if you want to estimate what is the error you can use, I mean some reasonable range, because just to be equal, it's always a question, what does it mean equal? You have always reached some reasonable equality, so there is always some error. There is some coefficient which is called spectral mismatch coefficient, which is used to estimate this adjustment. And actually, for single channel simulator, this spectral mismatch coefficient is used to adjust intensity. It's quite complicated formula, you can see, but it's much more easy to realize using this formula. I mean, just relation between short circuit current of the solar cells and the simulator and short circuit current of the solar cell under reference condition. Of course, this is a calculated value, and the same relation between short circuit current and the reference condition for the reference solar cell and short circuit current of the reference solar cell and the solar simulator. So just you see across of the relation, and then you simply can estimate the intensity, so you know the intensity of the reference solar cell and the simulator for each junction. Actually, so first of all, you have to calculate this coefficient for each junction. So as told you, if you have only one cell, it's only one junction. So if you have two junctions, so you have to calculate two coefficient. Then you have a check if your condition, the difference between this coefficient and 1 is less than 1, 0.2 0.01, so it's like a 1% difference between a unit. So you see, if everything is equal, you would have a 1. And this difference between this coefficient and 1, if it's less than 1%, it's okay. So you see it's quite strict condition. And then you have to find which subcell is limiting of the photocurrent. And for this subcell, you can adjust the intensity using this formula. So the current of the measured current of the reference subcell should be equal to this. This is current of the reference cell under reference condition divided by this coefficient. So you see the difference is quite small. So you should divide this value by something which is quite near to 1. But it's, if you want to produce perfect measurements, this is the rule. Just another thing, I would like to demonstrate another quite different approach. So here I'm speaking how to difficult to calibrate the intensity of the solar simulator to make a correct measurement of the multi-junction solar cells. But if you have a look to the measurement of the concentrator solar cell, multi-junction concentrator solar cell, you can see normally this dependence. This is an example from one of the publication, but it's quite conventional way to present the results. Actually, you see here some parameters like VOC, fill factor, and efficiency. You can ask why there is no current, and the reason is quite simple, because for this kind of measurements it is supported, so supposed that the current is linearly depends on intensity. It's one of the key point of this kind of measurement, because actually for this concentrator measurement, here you have a design of the concentrator cell. I would say cell of the module. It's not a solar cell, but some kind of cell. So when you have a Fresnel lens and you have a concentrator light, and again, if you want to measure parameters of the concentrator solar cell, you have a quite small cell, and as I told you, you have a simulator with not really homogeneous, spatially homogeneous light, and then you change the intensity. And in this case, actually, the values of short circuit current is calculated from a spectral response, and you know already the short circuit current, and people make an opposite thing. If you know the short circuit current, then you can say which intensity the short circuit current of the test solar cell, of the measured solar cell. There is no reference solar cell for this case, because it's like your measured solar cells is already some kind of the reference. And then you say, okay, for this short circuit current, I know it's one sun, and they calibrate the intensity. So it doesn't mean that they calibrate, they change, but it's just to some example. Then we can simply change the intensity, some random changing, and say, okay, this point is, for example, don't know how many, let's say 20 suns. So you should understand that when so it's some kind of slang. When we told about 20 suns, it means that density corresponds to the, because sometimes people do not really understand what we mean. And so I would say here is a quite different, it's in opposite. So you know the short circuit current of your solar cell, and you say which intensity of the simulator you have. It's another thing, because actually people are interesting not for the parameters under one sun, try to understand. They do not want to measure the IV curve at one sun to determine short circuit current. They already know this value, but they won't understand what happened when you change the intensity, and then you can plot this concentration dependence, which normally have such a dependence. I mean, it's very, you should stress that here we have a logarithmic scale. So when I told that the current, short circuit current, is linear, has a linear dependence on intensity, it's nothing to do with this curve. So you see, this is a logarithmic dependence of VOC. So in this case, short circuit current should have such behavior, like because it's linear. And VOC has a logarithmic dependence on short circuit current, because actually it comes from the ideal dependence of IVQ, from its ideal formula, from exponential behavior of the voltage on the current. So, but if we switch again to conventional problem of the measurement, not a concentrator solar cell, but some multi-junction solar cell, I would like to speak about two additional parameters, how to can we estimate the spectral match. So there are two additional factors which we call the of spectral mismatch. One of them describe how the spectrum of a simulator is different compared to the reference spectrum. For the measured solar cell, for some specific solar cell. I mean, you can imagine, for example, the case, as I told you, that we have some simulator, some LED simulator, which can be used for measurement of the silicon solar junction, solar cells. Yeah? And in this case, for example, we can use spectral response of the silicon and see what is the difference between this spectrum of the simulator and the reference solar cell. In this range of sensitivity of silicon, for example, difference is quite small, so we would have here a quite small value. And in the range when this difference is significant, the spectrum response is 0. So in this case, this parameter would be quite low. I mean, there is another way to present it. It's some kind of normalized parameter, because here we can say it's my large, small. It's a little bit easy to estimate. It equal to 0 if our spectra are identical, and it's equal to 1 if there is nothing to do with them. I mean, for example, again, if I'd like to measure some kind of low band gap material solar cell, for example, germanium solar cell, using a simulator which has quite narrow range of the intensity, only visible light, and my subcell is blend in this range because it's not the reason. It was not the reason to optimize. It was just in infrared spectrum. In this case, even if the spectrum are identical in visible range, I would have here some zero sensitivity, but when I have a sensitivity of my solar cell and in the range where there is a quite small large difference, and in this case I would have here the maximum mismatch. I mean, it's just to estimate not only the difference between a simulator and reference spectrum. You can see that, okay, but we can just have a look to the spectrum and realize, even, for example, we can make some comments, even take in mind some spectral distribution of each solar cell, but this parameter is really useful to make some not qualitative but quantitative estimation. And because when you have a choice, for example, of two simulators, which one would be used for the measurement of some specific solar cell, you should have some not just a feeling, not just some qualitative estimation, but you have to use some quantitative estimation. And similarly, another parameter which is used to estimate if our reference solar cell corresponds to the measured solar cell. Again, we have some condition. It's like we have some distribution of the intensity, and we have a look to the difference between the spectrum. So it's quite similar thing. You see, if you have two solar cells with identical spectrum in the range of our solar simulator, and they have some difference, huge difference in the spectrum, but there is no light in this range of spectrum, so it's okay. I mean, you can use it. There is no problem. For example, if you have some simulator which has some reasonable light, and then it has some simulator like this, and we have so for example here it's 0, yeah, see, and two reference solar cell. One of them has some spectrum like this, another one it has a spectrum like this. So we see there is a huge difference here, but if there is no light, there is no problem. I mean, for this spectrum. In contrary, if you have two identical spectrum like this, one like this, another one like this, and so simulator, for such simulator, no problem. But this, if the simulator would have some intensity here, you would get a huge problem. And using this formal parameter, we can estimate it. So there is some table to summarize what kind of parameter we can use using, for example, if we know the spectral response of the reference solar cell, and we know spectral distribution of this reference spectrum. So we can calculate the current of the reference solar cell, the reference spectrum. And if we have two different spectra of simulator and the reference, so we can calculate F1 for reference solar cell and for test solar cell. So again, if you have two spectra, we can calculate F2 for each spectrum, and if you have everything, we can calculate this just to summarize. And the most say important thing is here is I would demonstrate some example how to choose the correct reference solar cell. So, but first I would remind the main requirement for choose of the solar cell of reference solar cell. So one of the main requirements is a spectral match. So some general cases we have in ideal cases we have to use a reference solar cell with identical spectrum. For example, for double junction amorphous hydrogenated silicon microcrystalline silicon solar cell, it would be nice to use two reference solar cells based on amorphous and microcrystalline silicon. They have a nice spectral match, but we cannot to use them because, for example, for amorphous hydrogenated silicon we have a degradation. So light-induced degradation, and it means that its characteristics change with time. So, of course, we cannot use such material as a reference solar cell. It should be stable. Therefore, we have to think about more stable material like a crystalline silicon, the most available and stable. So, but what can we do? The simple solution, and we have a microcrystalline silicon. For this spectrum we can use just some crystalline silicon solar cell, reference solar cell, and for amorphous silicon we have to cut this part of the spectrum, you see, using some filter, some optical filter. If we have a look to this factor 2, you see in percent, you see that it's not so small, 21 and 34%. It's not really nice compared to what we want, because actually we want the 0. See, it's not really 0. So now we can think about how to improve our set of the reference cells. And one of the way to correct the spectrum of a solar cell is to use some set of the filters, of the glass optical filters. And here is one of some results. It's real experimental data, results of the work. People find some nice solution to match the spectra of both subcells. So you see here for microcrystalline silicon there is some crystalline silicon with some combination of filter, because you have a cut here and cut here. So compared to this, you see, it's quite. So this is the silicon. We start from the silicon, and here we cut here and cut here. So it's, and For amorphous hydrogenated silicon, it's another filter. You see, which cut most part of the light in this long wavelength region. Actually, it's the example of the nice fit, and actually, I can demonstrate the set of such spectra, the different spectra, but just looking for them, you cannot say that what would be nice, what would be better or not. It's quite difficult. But using the numbers, if you make some calculation of the factor 2, you can make some estimation of each combination of filter. So here you have results of this calculation. For example, for top junction, there are two. So the first one is filter 1 I have demonstrated before. It was this 21% for this reference condition. And actually, as I told you, we can calculate this factor for each specific simulator. Here, 3 types of simulator were considered, and you see there is some difference, but it's not so important. Again, for this filter 2, we have a value of 6.6%, which is quite nice. I mean, at least compared to 21, it's very nice. And again, you can have a look at what happened with the different simulator. And it's a little bit more, it was more complicated because there are a lot of work. You see here, there is a set of a different combination of the filters. And here again, we can select one best solution which provides a better F2. And now, if you have a look to the spectra of different simulators, so they're different. And what would be nice, it's not so easy to say, but if you have a look to this F1 calculated, now again we have different filters, and now we have calculated F1, so it means that we have calculated is it the difference between a simulator, the intensity of the simulator, and a reference spectra for each solar cell. So here you can see that, for example, simulator number 1, it's not best solution, I would say, that we have a simulator, for example, 3 or 2, which could provide a much better spectral match. And now we can have a look to this factor M to get the idea what we can use for calibration, for the correct measurement. As you remember, the main criteria was that the difference between M and 1 is less than 1%. So I have selected the corresponding set. So for example, here, as I told you, for bottom junction is a simulator 2, bottom junction with a combination of filter 1, and unfortunately for top junction it's not really the case. So it's much more complicated if you want to calibrate the intensity to measure multi-junction solar cell. And so here you can find some summaries of the table. But what I'd like to say mainly from this part of the lecture, that to calibrate the intensity of the solar simulator, you have to use the reference solar cell. It's more or less easy if you have a one-junction solar cell, but if you have a multi-junction solar cell, the things becomes more complicated. So at least you have to use the set of the reference solar cells. So I think it's all for now.